Hello, I'm Professor Tim Smith, and along with my student Claire Essex from Birkbeck, the University of London, and our colleague Teodora Gliga, we'd like to present to you our work today on understanding the differential impact of children's TV on executive functions and narrative processing analysis. So this presentation is going to be in two parts. The first part is going to be looking at how does digital media affect children's developing attention and learning skills over the first few years of life, and the second part is going to be a deep dive into a potential way of doing a formal analysis of kids TV, so we can start to understand which features of the kids TV may be directly impacting individual children's cognitive function. And the reason we're doing this is because of an observation which any parent will have had if they've switched on any of the many children's TV channels over the last few years, which is that kids TV is just really weird. The decisions the creators make in terms of the format they use, animation, stop motion, live action, puppeteering, the colour palette, the intensity of the kind of characterization and the narrative progression. There's just a lot going on in kids TV, which for myself, who's interested in cognitive film theory and also psychology and particularly cognitive development, I'm fascinated by how bizarre kids TV is, and whether analysing it in detail can actually tell us something about the developing mind and also tell us something about the insight that the filmmakers have had into making content which is particularly compatible to the developing mind. So what we know from decades of research into kids TV is that there are various factors you need to consider. The cognition of the child is developing rapidly over the first few years of life, but continues to mature throughout adolescence. So when you're thinking of kids TV directed to preschool age, there's a lot of impoverishment in terms of the cognitive capacity they have for understanding the screen-based content. We know that children younger than 18 months don't even differentiate between scrambled and unscrambled TV footage. They can't even tell when a program has ended and the advert breaks have started. They don't show any change in their interest to the screen. Up to the age of 4, they also demonstrate what's called the video deficit effect, which is that if you try to teach them content from screen media, traditionally composed screen media, they will find it difficult to transfer that content into the real world compared to if a face-to-face educator is doing the same thing, even if you try to match the visual features as much as possible between the pre-recorded and the face-to-face. It needs some kind of interactivity, some kind of response to the child in order to actually get them to transfer the information. So they're having difficulty comprehending what's on the screen and porting it into the real world. It's only by about 12 years of age that children actually start to show adult-like understanding of most scenic conventions used in TV film, the kind of cinematic conventions used for actually composing scenes. Children can follow kids TV, they can understand it, but they aren't able to reflect on the actual meaning of a lot of the content. And it appears to be that the content creators have intuited these limitations and are designing their content in a way that kind of simplifies and aids the understanding to the developing mind. They do this utilizing various features that enable the children to maintain engagement with the content, increasing the opportunities for learning of what's on the actual screen. And we're going to look at some of these over the next few slides. So how does screen media actually do this? How does it differ to adult screen media, and how might it actually maintain attention and simplify the processing? Well, this is a question that my colleague Sam Wass and I asked back in 2015 in our paper in Developmental Science, and we thought, why don't we take a formal analysis approach using the computational tools that were available at the time and apply it to kids TV to try and see how did it actually differ on the featural level. So we took the top 5 TV shows, kids TV shows from the UK channel CBeebies, which is aimed at preschoolers, in one particular week, and then we also took the top ranked adult TV dramas from BBC iPlayer in the same week. We digitized those first 5 minutes of these clips, and then we went through and we did feature analysis on the clips. We identified the shot length by manually detecting cuts, the shot scale, so how close to the actual human-like characters. Of course, in kids' TV, it's often not a human. We looked at where the faces and the eyes were located in the screen. I'll say more about this in a second. And then we did basic feature analysis in terms of colour, luminance, and the congestion of features, how densely compacted they were in the image. When we did this, we quantified it for the kids' TV, and then we compared it to adults' TV. We started to see some confirmation of the differences that were apparent in watching the sequences. So in these bar charts over here, the blue are the TOTS TV, so the kids' TV that we identified, and then the adult TV are the red bars. Now, all of the adult TV was live action, so it was a bit of an unfair comparison to the kids' TV, which had a lot of animated content in it. So as a closer comparison, we also choose adult-directed TV, things like Rex the Runt and Mongrels, which is a puppet show with very adult comedy content in the UK, and so that we could have a closer comparison to it. And then we could look at each individual feature dimensions. So in terms of the cut length, what we suspected is that there would be a slower pace of the content, and this was reflected in longer cut length, longer shot lengths in the TOTS TV than in the adult-directed TV live action, but also in the actual animated content, the non-live action. When we look at the brightness of the content, the TOTS TV tended to be brighter, as did the adult-directed animation. When we looked at the colour intensity, both in the blue-yellow channel and the red-green-yellow, it was also more intense. So there was a broader colour palette, brighter content, but slower pacing of the stimulus. But we thought, okay, let's go one step beyond that. Now we know from my work on eye tracking and in general compositional principles in filmmaking that the object of interest in most shots is going to be a speaking face, and in that face it's going to be the central eye region. This is what we usually compose shots to. So we can actually assume that in most shots that is what the centre of attention is going to be. So any designer of the content is going to want to capture attention and draw it to that region. Now we know that developmentally, preschool children, babies and toddlers, they struggle in parsing an image. They don't have the cognition and the experience that we have in order to actually hypothesize what objects are and parse them from complex backgrounds. So perhaps the designers of the kids' TV have been simplifying their composition to try to guide attention to this speaking face as a way of trying to get them to look at the most important part of the scene. So we went through and we manually coded the face region in the frames, and then we identify how well that face region can be categorized by the different feature dimensions in the TOTS TV and in the adult TV. And we do a method from signal detection theory where we calculate the area under the curve, which basically means that the closer this value is to 1, the more able it is to predict the location of the face compared to random locations that we've selected here. And when we did it for flicker, which is the low-level change in the image from one frame to another, we find that this is more predictive of the face location in the TOTS TV than in the adult TV. When we look at how congested the features are, so how densely populated the particular features are in that part of the image, they're higher in the TOTS TV than the adult TV. And we also found that the flicker dispersal, which here has been shown to be predictive of the face location, the dispersal, so how spread out it is around the screen, was also narrower, meaning that we had a lot of sequences like in this sequence from In the Night Garden, where the Tomley-Boos are dancing around in a relatively static shot. So they're the only source of motion. There isn't much motion in the periphery, so there's very low dispersal, meaning that the child can attend to the Tomley-Boos just by picking up on the motion. They don't need to do much parsing of the image. Whereas in comparison, when we looked at the adults TV, there was a lot of camera movement, there was a lot of peripheral motion, which distracts attention and makes it harder to parse. So this suggested that the TV designers of the programs were actually composing it in a way which would optimize attention to the points of interest. But once you've got there, you still have to make sense of it. That means you have to be able to extract the information and build an internal representation of it over time in order to comprehend the narrative. And this brought us to the work of Lillard and Peterson, who had done a series of studies where they were arguing that kids' TV can often be detrimental for the processing of content by the choice of the way in which it's composed. They had looked at a series of commercially available kids' TV programs, things like SpongeBob SquarePants, Caillou, or in this example here, Martha Speaks. And they believe that some of the content might be too intense, or might in some way fatigue the processing of the child, make it complex for them to make sense of it. So to give you an example, one of the features they were interested in was what they call fantastical content. So here's an example from Martha Speaks.
Other books too. Remove? You mean the words were taken out?
Sí, removidas. Removed, leaving nothing but a blank space. This is the adventures of Tom Sawyer.
Port, now men, with the wheel. Steady! Steady it is, sir!
In chapter 13, the word raft has been removed.
Ah!
It's just not the same if they swim down the...
So here, what was critical was the sudden disappearance of the raft, the fact that it violated the laws of space and time and physics by suddenly disappearing. Now, it was identified by Lillard and Peterson that this often happened in kids' TV, where there was breaks with reality, and they believed that considering how developmentally immature the children's cognitive processing is going to be of the expectations of the real world, that any time there's a violation of expectation, it's going to create even more demand on processing. They thought this might be detrimental in how they're making sense of the content.
Other books too.
So they ran a series of studies looking at executive functions. Now, executive functions are a suite of cognitive facilities that we all have, but we develop over the first few years of life. They're believed to be in a very nascent form in infancy, and then start to manifest around 3, 4, 5 preschool age, at which point they become incredibly important for a child to be able to discipline themselves and concentrate when they're in a learning environment like at school. So these functions include inhibitory control, interference control, working memory, cognitive flexibility, and rule maintenance. Things that actually you have to control your behavior and limit distraction so you can focus on what you're doing. They can be assessed in various little games, such as instead of doing head, shoulders, knees and toes, that the children are told to do a reverse follow, where if the instructor says, when I say touch your head, I want you to touch your toes. When I say touch your toes, I want you to touch your head. It's very hard for children to do this because they have to inhibit their prepotent desire to follow the normal rule and do something different. And it requires this inhibitory control and cognitive flexibility. Also, tasks like the Tower of Hanoi, when you have to stack these rings in size order by moving them between the poles. Or the most famous one is the marshmallow test, where the child is shown a marshmallow, the experimenter leaves the room and says, if you can sit and wait for this without eating the marshmallow for a set period of time, when I come back you'll get 2. And you see whether or not the child eats the marshmallow, which a lot of them do. So these are very behavioural, very naturalistic assessments of executive function. And when Lillard and Peterson did this, they found that shows that had more fantastical content actually led to poorer executive function after watching an episode, like a 9-minute episode of something like SpongeBob SquarePants, than if they found another show like Caillou or something with slightly more educational content that had less fantastical content. And they believe that was actually leading to a fatigue in executive function, a lowering of cognitive resources available to actually take part in these tasks after the study. So we're following up on this line of research by doing more precise lab-based studies. And one of the problems with Lillard and Peterson's work is they're comparing one episode of SpongeBob SquarePants to a completely different show. There are many ways in which they differ. They differ in their look, they differ in the content, they differ in the appearance of the characters, they differ in the narrative complexity. There are many things in which they differ. But in their prior studies and in the literature more broadly, they've just been categorized as being a show which has more or less fantastical content, or in some lines of research they've also looked at the pacing. So how much does new information get introduced, and generally this is seen as a proxy for it is seen as being the shot length. So they take a single dimension, they attribute it to a show, and they compare one show to a completely different show. Now, we'll know that when you're doing feature analysis or some kind of formal analysis of film, it's very hard to compare one show to another, one film to another. It's basically comparing apples and oranges. So in our studies, what we're doing is actually taking content and then matching it whilst changing the fantastical nature of it. And to do this, we've used Looney Tunes, which is not familiar to our toddlers that we're going to use in this study. We've selectively chosen moments which are less violent and are less culturally inappropriate, which unfortunately a lot of it is. But we find these rather mundane sequences. And then we have on the left is the non-fantastical content, so it's typical Looney Tunes fare. And then on the right we have slightly later sections from the same sequence, where something happens that violates the laws of physics, like Daffy Duck suddenly being in multiple places at the same time. And so we've got fantastical moments whilst controlling everything else. And we're going to be looking at the direct impact that these have on the children's executive functions, but instead of doing it in just behavioral tasks like this, we're actually going to be monitoring cognition as they watch the sequences, and then the immediate consequence on attention, working memory, inhibitory control, and learning. And we do this using a series of eye tracking tasks. We have a visual search task where they have to be able to deliberately focus attention in order to find a target which either pops out or to deliberately search for it amongst distractors. They have this task which is anti-saccade, where a flash appears and they have to learn to inhibit to saccade to the flash and look to the target, because only at the target will they get the reward. You'll see an example of this in a second. And then we also look at learning tasks, where they have to learn names associated with novel objects to see whether or not watching the fantastical clip, which is matched in visual content, to the non-fantastical is going to directly inhibit these processes. So unfortunately, due to the pandemic, this study should have finished data gathering. We would have had results to present to you, but unfortunately the labs shut down. We were unable to test for about an 8-month period, and so we've only got preliminary data on this right now. But what we do have is an example of what it looks like for an 18-month-old here, who were being watched with a webcam, and this is the gaze data. So the green and the blue squares are the location of the left and right eye, and the red is the Euclidean average of the two. And you can see how her gaze is zipping around the screen, updating with the new content, tracking the animals, trying to find their eyes over time. So you can see how actively she's engaged, except at this moment when she's obviously zoned out. When she's engaged with the content, and then immediately afterwards we can see her doing the task. So this is the anti-saccade task. You can see that there's a black flash that she has to not look at, and then she has to look at the rewarding content on the opposite side of the screen. And so from this we can get online measures of her executive function. And this study is ongoing, and we hope to be able to present this work to you in the future. So one project we've done in the meantime, whilst waiting out the pandemic like the rest of the world, is taking a different approach to studying the kids' TV content, where we're trying to take a multi-level narrative processing approach to content that has been shown to deplete EF executive functions. And we're doing this within the SPECT framework. So along with my colleagues Lester Loschke and Joe Magliano and Adam Lawson, we have developed what we call the Scene Perception and Event Comprehension framework. Now this is a cognitive framework that we apply to understanding how screen media may impact viewers at multiple levels of processing. And we've used it to understand how they process various films, including things like Touch of Evil and James Bond's Moonraker. But here we're applying it to kids' TV. And what it enables us to do is actually to formalize different levels of the content and consequential levels of cognitive processing. So what we have is a distinction between what we call the stimulus features, which are agnostic features you can identify in the stimulus, like the flicker and the edge density, which are also approximations of what we know is going on in the early visual cortex. And then front-end processing, which is how these features may relate to how we shift attention over time. We choose to fixate, we shift from one point to another. And we distinguish this from back-end processing, which is the cognitive representational level of processing, which requires maintenance of information in working memory, executive processes, including inhibitory control and goal setting, and then the representational levels in our event model. So this is within the event segmentation theory put forward by Jeff Sachs, where we extract certain features from any narrative content in order to construct a representation of this over time. And so we can identify all these different levels that are evident in the actual film clips. Some of these we can automate. So when we're looking at the initial stimulus features, we can use code in order to process the digital features and pull out those features. So here we've got an episode of SpongeBob SquarePants. This has been passed into edge information, and on the right we see the flicker, which is the change of this over time. On the plots here we have the change in the actual edge density as it's going up or down with the complexity of the image, and here we have the actual motion signatures in two different forms, in flicker and in a correlation a measure which comes from James Cutting's work. So we can see how each frame is actually leading to these low-level feature changes. And we can do it for the clips like SpongeBob that have been shown to be EF depleting, and we can do it with a show which is not, from Kalu. And here we can again see the actual compositions extracted into edge features and how they change over time. And what's noticeable here is how clear the cuts are in a lot of the sequences. So when there's a cut, you get a large spike in the actual flicker, and you get a bit of a change in the actual edge density because the composition of the shot changes. So what we've done is we've done a reanalysis of the stimulus that Lillard and Peterson and subsequent colleagues have used across their studies. They state exactly which episodes they've used to show to kids and then see whether or not they result in EF depletion. And so we found those episodes as much as we could, and then we run our level of analysis on it. We process it at these stimulus and low-level features like flicker, edge density. We extract shot length by manually coding the shots. And then we also coded higher order narrative processing features like the changes in situation that are derived from changes in space, time and action depicted in the sequences. Now these are known to be important features when you're identifying the narrative moments, also event sequences, and consolidating that information to memory. So by tracking these features, we get a sense of how complex the information is, how much it's changing over time at the narrative level. Now, as I said, some of these can be done automatically. The flicker, edge density can be identified automatically, but the other features we did manually because tools are not advanced enough to be able to do that right now. And we applied it to the sequences we could find from Lillard and Peterson. So we have those which are shown to be non-EF depleting, Kalu, Phineas and Ferb, and 2 episodes of Arthur. And we can quantify the feature dimensions that were extracted across these whole episodes by our analysis and compare it to those which were EF depleting. So the basic assumption would be that if we took shows that were more EF depleting, then they're likely going to have more intense features. They're going to be changing faster over time, may have a higher level of those features. And so that's what we looked at here. We looked at how much change there was in the image over time, and we found that by and large the average across all of the EF depleting was that they were a higher level of flicker. There was more change in the image. We thought, well, that could also be a correlate with the pacing, because Lillard and Peterson had that as one of their manipulations. They chose sequences that they had short shot lengths, so had a faster pacing, versus those that had longer shot lengths, a slower pacing. If you have more flicker, you get high levels of flicker across each cut, so the faster the shot length, the shorter the shot length, the more flicker you might get. So we separated those two. Looking at the shot length here manually coded in these sequences, we actually found that the non-depleting sequences were actually of shorter shot length than the depleting sequences, meaning that those that were depleting actually had longer shots slower pacing. That was really quite surprising, and was also contrary to what Lillard and Peterson said when they specified what the pacing was of these sequences. Now, for a lot of their analyses, they did this using a shot detection tool, which actually processes the low-level flicker of the sequences and hypothesizes where cuts were going to be. But we know from a long line of research from cinemetrics, people like Barry Salt and James Cutting, that if you use these low-level feature detectors to find cuts, there's a lot of anomalous cuts there. Camera movements, sudden zoom-ins can be attributed to being cuts when they're actually not. So what we think is that in their existing studies, they've got some anomalous recordings here. And we also looked at some other feature dimensions. So edge density is how complex the features are, and there's not much difference between the non-EF depleting and the EF depleting. And then at the higher level of situational change, we found that generally there are more situational changes in the EF depleting than the non. And what we then did is we z-scored each of these measures, which is a way of normalizing them onto similar scales, and then we summed them up across all the different feature dimensions to see whether or not there was a cumulative impact of these features on whether or not a show was seen as EF depleting or not. In general, across this relatively low number of clips we have here, which is too few for us to actually do statistical tests on these, we found that the non-EF depleting had lower cumulative feature scores than those that were EF depleting. Now what this means is that even though these shows are categorized as being either fantastical or not, they're actually distinguished on many different levels of features. They're distinguished on the basic image features and on the situational change narrative features. Fantasy is just one aspect of that is also correlated with a lot of these other design decisions that the filmmakers have put in. So this is a confirmation of what is actually quite evident. If you take a show like Caillou, it seems quite simple, it's kind of calming and slow-paced. Whereas if you get something like SpongeBob SquarePants, it's just in your face all the time. So yes, it's more fantastical, but that's just a shorthand to say it is very, very different and very intense. And what we hope is by actually taking this multi-level narrative processing approach, we can show that it's important to consider each of the design decisions across the whole range of the production of these shows. So can we actually take these analyses to look at existing content or work with content creators to help them guide their decisions about how complex they compose the shots, they can compose the pacing, and they compose the actual narratives to make it appropriate to individual developmental levels and also minimize the impact it might have on executive function. Because it's only by enabling the children to have residual cognitive resources that you get learning, that you'll get successful functioning with the information after the TV content. So in summary, what we've presented here is that the cognitive skills needed to process screen content show a protracted developmental period during development. The unique scenic language that has evolved to aid children's engagement with the content has been validated and shown through our series of studies, both in terms of the eye tracking, but also in the feature analysis. But these conventions have differential impacts on children's cognition and executive function, which again will likely change over time and with age. And understanding the behavioral consequences of viewing different types of content can only be achieved through operationalization of the features and empirically testing them, which is what we're trying to do and also promote to others to do in more detail. So thank you. I'd like to thank all the babies and the film TV content providers, my collaborators, mostly Claire Essex, the student for leading on this, and our collaborator Teodora Gliga, as well as my funders and my researchers. Thank you.